Yeah. Top is the 3090, bottom is the A100.
Wow, that is a crap ton faster than the 3090.
It's pretty much the same as the CMP, but look at the efficiency.
714 kilohash per watt.
And I bet you if we lower the power limit to like 80, it's a little bit lower speed.
Yeah.
Maybe we can go, I don't know, we probably don't have to tinker with this too much. It doesn't draw that much power to begin with, I guess.
Yeah, I think it's pretty freaking efficient right out of the box.
I mean, the efficiency is better, a little bit better. But before it was doing 175 megahash roughly at 250 watts, so pretty damn good. 3090, you can probably do like 300 watts with 120 megahash. We're running the folding client now. I've had it running for a few minutes, and it's kind of hard to say. The thing with folding is based on whatever project you're running, which is whatever job the server has sent you to process, your points per day will be higher or lower. So it's possible that the A100 got a job that rewards less points than the 3090 did.
Right.
It does look like it's a bit higher, but you can see our 39, this is like a little like comparison app thing, is 31% lower than the average. So it's probably just this job doesn't give you that many points.
Got it.
The interesting part is the 3090 is drawing 400 watts.
400. Holy
The
shit.
A100 is drawing
240. Man, that's efficient. And performance per watt, maybe gamers don't care that much. Actually, we know for a fact gamers don't care that much. In the data center, that's everything because the cost of the card is trivial compared to the cost of power delivery and cooling on a data center scale.
Especially when you have 8 of these with a 400 watt power budget like you would get on the SXM cards in a single chassis times 50 chassis. Like, that's a lot of power.
Let's try something machine learning.
Unfortunately, for obvious reasons, most machine learning or deep learning, whatever you want to call it, benchmarks, don't run on Windows. So instead, I've switched over to Ubuntu, and we've set up the CUDA toolkit, which is going to include our GPU drivers that we need to even run the thing, as well as Docker and the NVIDIA Docker container, which will allow us to run the benchmark. We're going to be running the ResNet 50 benchmark, which runs within TensorFlow 2. This is a really, really common benchmark for big data clusters and stuff, except our cluster, it's just one GPU. In a separate window, I've got NVIDIA SMI running. It's kind of like the Linux version of MSI Afterburner, but it's made by NVIDIA, so not quite. But what it's good for is at least telling us our power and the memory usage, which we should see spike a lot when we run this benchmark. I took the liberty of pre-creating a command to run the benchmark, so we're going to be running with XLA on to hopefully bump the numbers a bit. We will do that for the A100 as well, so no worries there. It should be the same, as well as using a P1. Look, he left because he didn't have time for this, and now he's back. This is the world's most expensive roller. I don't even remember what I was saying, damn it. Distractions aside, we're going to be running with XLA on. That'll probably give us a bit higher number than you would normally, but it is still accurate, and we're going to be running the same settings on the A100 as well, so no concerns there. We'll also be using a batch size of 512, as well as FP16 rather than FP32. So if you want to recreate these tests yourself, you totally can. Let's see what our 3090 can do. Look at that. 24 gigs of VRAM completely used. I don't know if there's any application aside from like Premiere that will use all that VRAM. I'm sure Andy can attest to that. Okay, 1,400 images a second. That's pretty respectable. I think like a V100, which is the predecessor to the A100, does like less than 1,000. So the fact that a 3090, which is a consumer gaming card, can pull off those kind of numbers is huge. Mind you, the wattage, 412 watts. That's a lot of power. It'll be interesting to see how much more efficient the A100 is when we try that after. The test is done now, and the average total images per second is 1,435. It's pretty good. I've gone ahead and added our A100 so we can run the benchmarks on that instead, and I'm expecting this is going to be substantially more performant. So it's the same test. I'm going to run the command here. I'm going to wait a few seconds. We got NVIDIA SMI up again. You can see that it's just running on the A100. The RAM on the 3090 is not getting filled. We're just using that as a display output. You see all 40 gigabytes used. That's crazy. If we thought the 3090 was fast, look at that, Andy. That's like a full 1,000 images more. We're getting like 2,400 instead of 1,400. And the icing on the cake, it If you look at NVIDIA SMI, they're using like 250 watts instead of 400, while getting like almost double the performance. That is nuts.
Probably the coolest thing about this whole experience, though, is seeing the Ampere architecture on a 7-nanometer manufacturing process. Because you got to remember, while none of this is applicable to our data business, what this card does do is excite me for the next generation of NVIDIA GPUs. Because even though the word on the street is that the upcoming Ada Lovelace architecture is not going to be that different from Ampere, consider this. NVIDIA's gaming lineup is built on Samsung's 8-nanometer node, while the A100 is built on TSMC's 7-nanometer node. Now, we've talked a fair bit about how nanometers from one fab to another can't really be directly compared in that way, but what we can do is say that it is rumored that NVIDIA will be building the newer Ada Lovelace gaming GPUs on TSMC's 5-nanometer node, which should perform even better than their 7-nanometer node, and if the efficiency improvements